Recording is on.
Good. So I guess we can start. Some more people probably are going to join us in a few minutes, but we can just start with some welcoming and housekeeping. So welcome again, Professor Van Boekel, and thank you to all of you who already joined us today. And welcome to today's session of the webinar series organized by the Young International Committee of Predictive Modeling in Food. The Young Committee is a global initiative which works in the framework of the International Committee of Food Predictive Modeling in Food, and is a global initiative of early career scientists working to promote education, collaboration, and knowledge sharing in the field of predictive microbiology and food modeling. This is a free open access webinar and is part of our mission of build a strong international community by connecting students, researchers, professionals with experts in the field. And we're really happy that you join us today, whether you're joining in live or you're listening to the recording. And I'm very happy to welcome also Professor Tini Van Boekel, which offered to lecture us today. So before introducing him, I will just give some housekeeping rules just to make sure that everything goes smoothly. As you may have already seen, this session is going to be recorded, and both the video and the presentations that you should have already got in your email are going to be shared with all the participants. As you notice, you have your microphone and your camera muted, so please keep it so during the talk to ensure that the audio is clear for everybody. You can type any of your questions in the chat box. We will monitor the chat to make sure that we capture all of them and share with Professor Van Boekel at the end of the session during the Q&A. Feel free to engage with us via our Slack community or the LinkedIn for updates on upcoming webinars. And if you have any technical issue, try to write in the chat, and we'll try to assist you as soon as possible. So now, without taking any more time, I will introduce our speaker, which is, as I said, Professor Tini Van Boekel. Professor is an emeritus professor in food science at Wageningen University in the Netherlands. He has led research and education for decades in food quality, mathematical modeling, and dairy science mainly. And over his career, he has authored over 250 peer-reviewed papers and several books. He received the EFOS Lifetime Achievement Award in 2024, and today he walks us through a very interesting topic, which is the from basic statistic to predictive modeling in foods, including a frequentist versus Bayesian approach. And he will talk also about probability and linear regression. So without taking any more of your time, Professor, I will leave you the floor. And thank you again.
Okay, thank you, Federico, for the introduction, and welcome to all of you, mainly in Europe, I understand, but maybe also from other parts of the world. I'm very happy to see all of you on the screen. And I also would like to compliment you with your organization, because I think this is someone I would like to have had when I was young, to have such an association to work together and to learn from each other. But that did not exist in my time. So compliments for that. And I understand that most of you are early career scientists, and that is very hopeful that you are willing to participate in such a network and to learn more about predictive modeling. Predictive modeling is one of my expertise that I built up during my career, and I'm happy to share that knowledge as much as I can. So I will start my presentation, and I hope that will all work. Let's choose what to share. the entire screen, I guess. It does not want to open at the moment. This one. Yep. Okay, is it all visible to you?
Yes, we can see your screen. It's not in presentation mode. We can see the full app.
Oh, really?
Yes.
In my screen, it is a full screen. So you still see only see all the.
Yes, we see the first slide and also the panel on the side with all the other slides.
That's strange.
Yeah, sometimes it happens when you share the app and not the full screen.
Okay. Let's see. I have to go back here. You say to share the.
Yeah, usually if you share the whole screen and then go in presentation mode, it's visible.
But the whole screen does not want to share it at my computer, at least. That's strange.
Now we see the whole screen. Yes.
Okay. Now we should.
Yes, perfect. Now we see the presentation mode. Yeah.
Okay, good. Sorry for the clumsy start. Okay, so as Federico mentioned, we are going to talk about the role of statistics in predictive modeling, and let me first show you what I had in mind to talk about. The role of statistics in science, and that will be very brief because I will focus on the statistics. But I like to put it in perspective. So, what is the role of statistics in science, which is mainly about how to analyze data? I will talk a lot about variability, errors, and uncertainty. I will show two approaches that are available in science. Then I will talk about modeling and regression, about ANOVA and such things. And I like to highlight also the differences between these two approaches in statistics. Also, some remarks before I really start. We have 3 sessions of 1 hour. And my main goal is to share with you some developments that there are in the field of predictive modeling. But as I wrote here, I can only scratch the surface because 3 sessions of an hour is not much. There's much more to tell. So it will be mainly introductory, and I will only use very simple examples to explain some principles. And I think that most of you are food microbiologists, so I will not give many examples in your field, but very simple ones just to explain some principles. I will also not show you a lot about how to actually do it, because there's no time for that. So we also have no time to exercise, which is the best way to learn, actually. Yeah, ask questions if you like. Because of the number of people, it's probably easier to do that in the chat, and we'll come back to that after the first presentation. Having said that, I can only scratch the surface in 3 sessions. I'd like to point you to the course I'm going to give in a coming October, which I have much more time to explain all the things I like to share with you. And that will also include microbiology from our microbiological professors here in Wageningen, and it will contain a lot of exercises. And you have always also received the flyer. about this course that I'm showing here on the screen. So if you're interested in that, I hope you will also have the opportunity to join in Wageningen. It will be much more detailed than what I'm going to tell you today, tomorrow, and the day after tomorrow. But let's really start now. I wanted to say just a very few words about the scientific approach. As you're all early career scientists, so I guess that most of you, well, this is nothing new to you, but I still want to mention it because it gives me the hook to link it to statistics. So first of all, you always have to ask yourself, what do I really want to know? What is the goal of my research? So basically, what is the scientific question? And once you have that question, the next thing is that you have to have some idea about what is actually happening, so that we can call a hypothesis. If you have such an hypothesis, then the next question is, what do you expect if that hypothesis is true? So you can then think about the type of experiments that you need to do, or if you are a social scientist, you can also observe. You can think about the methodology that you're going to use, all based on your idea, your hypothesis, what the question is about. And then the next step is to do these experiments and to collect data. And these data should represent the reality. That is what we want to learn from the world around us. And you then need to confront those data with the hypothesis, which is basically your idea of the world. And I can almost guarantee you that mostly your data will not confirm your hypothesis, and you will have to think again. So this is the stage of criticism. If you have data, how do they match with your hypothesis, and how can you adjust your hypothesis to well, to come to better ideas? And what this really means is that you are learning from the data, and by this learning you can update your hypothesis. This is shown graphically here, just as a very simple view of how science works. There's much more to be said about this, but this is basically how, especially in the natural sciences, people tend to work. And the reason I'm showing it in this way is that it is an iterative cycle. It is not one cycle only. You always have to probably to adjust your hypothesis, and that is the phase of model building. Now, talking about models, what are actually models? Also that we can talk about for hours, but just briefly, here I like to say that we talk here about mathematical models, and mathematical means that we are capturing this reality as we think how reality is in an equation. And usually that can either be algebraic models or differential equations. Now, models are simplifications of reality, and therefore they are always wrong, but they are wrong on purpose. They are simplifications, so that's not bad. But it is always good to keep in mind that your models are only simplifications and not the whole truth or the whole reality. Now, here I give some examples of equations. The very simple first-order model in food microbiology. Modified Gomperst, if you want to talk about the growth of bacteria, or the Barani-Roberts model, which is basically a differential equation, just as examples what we mean by mathematical models. Now, in my view, there are two goals of modeling. First, to understand the mechanism that causes the data that we observe. So this goes back to the hypothesis idea. You have some idea about what is happening. Then you have the data, and we want to know, why are these data like they are? That's one reason. So it helps us to do science. The other goal is, once you have a model, is to make predictions for instance, to do calculations on shelf life or to do risk management, but there may also be other reasons to do this. And there you see sometimes wrong messages in the literature, because many people talk about prediction when you actually mean fitting. And a better word actually is retrodiction. This is a term I learned from Boekel. I will talk about him later. But retrodiction means that you are, in retrospect, confronting your data and the model. Prediction means that you are using a model to predict something that has not been observed yet. So if you fit a model to data, this is not prediction, because the data are there and you have built a model based upon those data. So it's wrong to call that prediction. I would rather call it fitting or retrodiction. And another thing that we need to think about hard is what is the predictive capacity of a model? Because if you have fit a model to data and then you leave it, you don't know how it will behave when there will be new data. So we really need data for building, for validating, and also for criticizing models. Now, if we talk about data as a scientist, we actually need to extract the information that is contained in these data in order to answer our scientific question. And now comes the problem, and also the reason why we need statistics, because we are always confronted with variability, with errors, and with uncertainty. And the question is how to deal with that. And that's why we need statistics. And I have one quote from a book here from Simon Vaughan, which I really can recommend. It's very nice. But he has a quote which I like: statistics is really how to deal rigorously with uncertainty. I think that is actually the essence of science, because we see many things that are uncertain and we need to make something out of that uncertainty. I should also say, by the way, that I'm not a statistician. I'm just a simple food scientist. But I learned that statistics is really, really very necessary in science. But having said that, I think I can also state that statistics is not the goal. It should not replace the science. That's the most important part. You really have to think hard about your hypothesis and how the data confirm that or do not confirm a hypothesis. So statistics, in my view, is only a means. It's not a goal. But it's a means to describe and summarize measurements, to separate noise from real information, to interpret the information, to evaluate the fitting, and to test the predictive capacity. Now, talking about a bit more about variability, there are quite a few sources, and I'd like to separate it at least in 3 sources. Probably there are more. But the first source is, since we are food scientists, we have to work with biological materials. And biological materials are always variable. They are never exactly the same. This goes for people, it goes for animals, it goes for plants, it goes for bacteria, it goes for the foods themselves. And this is just a property of the object. It's there, and we need to work with it, and we have to acknowledge it. Then, in our doing our experiments, there is another source of variability that we call technical variability. So if you would have one single source of that you want to sample, and that source is completely the same, and then if you repeat the experiments, you still will see variation, and we tend to call that errors, which I'm not completely happy with. I would rather say it's inexplicable variation. We can just not explain it, but it's there. So if you analyze 10 times the number of bacteria in exactly the same sample, you will get 10 different results. This type of variability we can again separate a little bit in precision and accuracy. I will show that in the next slide. But this kind of variability is not a property of the object, but it is a property of the method that we use to collect our data. Then the third uncertainty that we have is a property of the researcher, because we do not know everything and we cannot control everything. So this is definitely a property of the researcher. These concepts of I don't know if I can move this one. Yeah. These concepts of accuracy and precision I try to explain with this slide. So you all recognize this as something this where you can shoot with a rifle or something like that, or an arrow. If you all hit the center of this target, and they all come at the same spot, that means you are working accurately and precise. You can also have the situation like on the left side, at the right side of that picture, that you have very precise measurements. So they all are in the same neighborhood, but they are off the target. That means it's inaccurate, but it is precise. You can also have the situation at the left lower side of the screen, where you can have an accurate, on average, they enter in the target, but they are quite imprecise because they are scattered. And then the worst you can have is that you have inaccurate measurements and also imprecise measurements. So it's always good to try to find out how your data can be classified in that respect. Now, accuracy actually means how close is the value that you have measured to the true value. The true value, of course, we don't know because we want to measure it, and if we knew it, we did not need to measure it. So it is usually not known. But we can do something with calibration. So accuracy is actually more or less the same as the absence of systematic errors. Now, precision is something else. This is how close the measurements are together. And as I showed in the previous picture, you can be very precise, but still very inaccurate. So you really need to check where you are in terms of accuracy and precision. Then something that I keep on telling you, do not hide variability, because it is a very important source of information. And I see the tendency in literature, and sometimes also in presentations or with students, that they try to hide this variability as if it is something that you should be ashamed of. So you see a lot of work being averaged, but averaging, in my view, is hiding results. You should show the variation graphically and numerically. And what I want to work towards is that these variabilities and errors and uncertainties, they can be quantified, and they can be quantified in probability distributions. We will talk about that in a moment, but you always have to try to separate the source. Is it biological variability, or is it technical variability, or is it variability due to the fact that we do not know everything? Because biological variability cannot be reduced. It's a property of the object, and you can repeat experiments to characterize this variability, but it will not be reduced. But technical variability and the errors that result from measurements, they can be reduced by doing more measurements. So also that is therefore it's important to separate these sources of information. And I want to show you a very simple example. And as I already mentioned, you have to always state your goal. What is your scientific question? What do you want to know? And in this example of apples, it was a very simple goal. We want to learn how weight and size of apples are related. So in this case, it's very simple. You collect apples, you weigh them, and you measure the size of them, the diameter, and that is your data. Now, the first thing that you always have to do, whatever you're going to do later, is to plot results, visualize them. This is called explorative data analysis, EDA. And then a histogram or a frequency distribution shows how often certain measurements are observed. And here is an example of such a EDA where I have collected some samples of data of apple size and weight. I only show the weight here for the moment. And you can just count what the weight is in certain ranges. And then you get this kind of histograms, and you can calculate the mean, which is something like 88 grams, which is here, and the standard deviation characterize the variation in this. And this is definitely biological variation, because you can measure weight and diameter very precisely and accurately. So here we really see biological variation. And this is, of course, everyone's experience. Apples are not always the same. Now, such a histogram can be normalized. You just divide the number of samples in a certain range by the total number of samples, and you get a frequency distribution, which you can then link to a probability density function. We'll talk about that in a moment. This characterization of samples you can summarize with measures of central tendency. It can be the mean, which is mostly used. This is just the arithmetic average that I also just showed you, these 88 grams. You can also have the median. It's the value that divides a distribution in half. And you can also look at the mode, which is the most commonly observed value. So when you observe variation, you can calculate these most likely values, but you can also calculate dispersion around that mean, which we usually express as a standard deviation. And now, as you probably know, most observations, but not all, can be modeled by a normal distribution. A normal distribution you all remember and know, I imagine. It looks like this, and here below I have written the mathematical equation. And you should really learn how to interpret this equation. What it says here, it's the probability for data y given parameters theta. And in the normal equation, we have two parameters, the mean mu and the standard deviation sigma. So this graph shows you the probability for data given a certain value for mu and sigma. And in this case, the mu is 0 and the sigma is 1. This is called the standard normal distribution. But you really have to appreciate what this actually means. It just indicates when you know these values, what is then the probability to observe data outside these mean and dispersion values. So the normal distribution is used a lot, maybe actually too much. It is a bell-shaped symmetrical distribution with two parameters, mean, standard deviation, and also a characteristic is that the mean and the mode and the median are all the same. Another important thing to remember, and this is becoming relevant later, as we will see, it is for continuous data, and it runs in principle from minus infinity to plus infinity. And furthermore, it is a variation around the mean is additive. So it is mu plus or minus sigma, which means it's an additive property. Now, a normal distribution is one that is used most, but it is only one example of a probability distribution. The reason it is used so much is because it's simple to interpret. So if you have a mean, and again, this is the standard normal distribution with a mean of 0 and a sigma of 1. But if you have a mean plus or minus 1 standard deviation, you cover 2 times 34.13%, which in total is 68.26%. If you do 2 times sigma, you enter up here, 2 times 47.73. And if you have 3 times sigma, you have covered almost all of the probability distribution with 99.7%. And you will probably recognize that these are especially this one, the mu plus or minus 2 sigma is the 95% confidence interval. Now, going back to my apple example, weight of apples, of course, these are continuous data. The apple can have any value. It can be 88.1, and also 88.7, etc. So what we can do is we can turn this histogram, which is just counting how many samples there are in a certain range, to a frequency distribution by dividing it by the total number of samples. And then we can see in how far that distribution is described by a normal distribution. And well, you can debate whether or not this is a reasonable fit, but I think that this is not bad at all. So you could conclude from this, well, a normal distribution is not a bad choice to represent this the sample of apple. Why is the normal distribution so important? Well, you can prove that if you have many small deviations and you add, and they all add up, you get a normal distribution. But the problem is that sometimes it predicts negative values, because in principle it runs from minus infinity to plus infinity. And now we have our first problem here, because apple weight cannot be negative. We don't have apples that weigh minus 10 gram. So how can you deal with that? So here I have another set of data of apples, where which is a much bigger data set. And now you can see that the symmetry has gone. The apples cannot be negative. And you also see that there are also quite a few very heavy apples. There's a big tail to the right here. And if I now fit a normal distribution to this data, I get this red curve. And then you can see that, first of all, it does not predict the symmetry, because a normal distribution has to be symmetric. So it cannot predict this, this tail here. And it will also not predict well the mean, because it is shifted by these very large value here. And even more importantly, you can also see that it predicts negative values here. So in this case, and actually there are many cases like this, a normal distribution is not a good one. And then we enter the fantastic world of other distributions. And one that is actually quite applicable is called the log normal distribution. And when is a distribution called log normal? If the natural log of the data is normally distributed. And if a value x of a variable x is normally distributed, then an exponential of that variable will be log normal distribution. And the relation between log normal and normal is that if you take a log of a product, it ends up in additive, which is a property of the normal equation. So that's why it's called log normal. Here is the equation for the log normal distribution. And now you can see that these parameters here are now on the log scale. So don't make mistakes here, that these are not the original parameters for the original data. These are the log transformed parameters. Here I show the fit of the same data, but now also with the log normal distribution, and you see that it fits much better. So this is just to show you that don't limit yourself to normal distributions. And also be aware of that when you transform back, that additive errors on the log scale, they become multiplicative on the natural scale because of this exponentiation. Now, since many of you are microbiologists, I think, you are probably aware of the fact that most researchers do log transformation of data. But the question is that actually correct? Because what you count are not continuous data. You cannot have a 1.2 bacteria. So count data are really discrete. You can only have integer values. So plate counts are actually not continuous values. And there's another distribution that actually applies much better. That's called the binomial distribution, because what you're doing here is you are counting whether or not a bacteria grows. So it can grow or it cannot grow. And that's typically for a binomial distribution. And then there is a special distribution in the case of plate counts, which is called the Poisson distribution, which is actually a special case of binomial distribution. And the Poisson distribution is really much more applicable to count data because they are discrete, such as colonies on a plate, but also many other examples. The assumptions for the Poisson distribution are that the events are rare and occur independently, and the outcome is yes or no, growth or no growth, and the average numbers per unit area is constant. I talked already about the probability density functions. In the case of discrete data, we should not call it a density function because it's not continuous, but they should be called a probability mass function. So here you see an example of such a Poisson distribution for counts taken from literature, actually for plate counts. And another interesting observation is that you can actually have 0 observations, which is impossible if you take the logarithm because the logarithm of 0 does not exist. But with the Poisson distribution, you can actually take into account that there are 0 observations. There may be plates where you do not see growth, and you can count them. The Poisson distribution, the mass function is listed here. It has only one parameter, usually called lambda. And the nice thing is that it actually is the mean as well as the variance in one parameter. And it only works for positive numbers, which includes 0. And here you see some examples of how this distribution shifts if the mean is increasing. So the bigger the mean, the more it's going to approach a normal distribution. But for small counts especially, it is definitely deviating from a normal distribution. Now, why is it so important to have probability distributions? They reflect what you can say about the most likely values, or if you want, the most unlikely values of a quantity. And they summarize your data in terms of some parameters like the mean, the mode, and the standard deviation. And you can also use them to show visibly how your quantity of interest is dispersed. So it's really a very nice way of expressing variability or uncertainty or precision. And we will use that a lot in the second webinar when we're going to talk about regression. So once again, there are many more distributions than just the normal one. The normal one is very nice for continuous data between minus and plus infinity. But if you have data that cannot be 0, then the log normal distribution is a candidate. But there are also others like the exponential distribution and the gamma distribution. If you have discrete data like counts, then the Poisson, or a bit more extended, the negative binomial, is a distribution that is becoming interesting. And if you have proportions, then a beta distribution is valid because it just limits everything between 0 and 1. Here are some examples. The normal distribution, you already saw it. You can also have a uniform distribution, which means that every data within a certain range is equally probable. You can have a log normal distribution, as we saw, which typically has a right skewed distribution. Or you can have this beta distribution, which can only be valid for numbers between 0 and 1. So to conclude intermediately, there are many probability distributions that you can use. So don't limit yourself just to a normal distribution. Having said that, if you have larger means, the normal distribution will usually be a good approximation. And the nice thing is that all these distributions are related. They are called the exponential family, and depending on the conditions, they go either to a gamma or a normal or a Poisson or a binomial distribution. So once you are able to quantify variability with the probability distributions, you can make predictions. So you know the mean, that means, and the standard deviation, you can then start to predict what are the most likely values. Variation is usually expressed in standard deviation or the square of it, which is called the variance, which tells you about the expected variation in the data. And by the way, I like the term expected value, actually better than the mean, because it's something that you expect based on a model. What is then the most likely value? There are some other concepts that you need to know of. One is the standard error of the mean, which basically says how precise, not accurate, but how precise can you estimate the mean. And this is the formula for the standard error of the mean. It's the standard deviation of the distribution, the estimate of it, divided by the square root of the number of observations that you have. And what you can see here is that the higher the number, the smaller the standard error of the mean will be, which means that if you do more measurements, you will better be able to estimate the mean. But you have to make a difference between the standard deviation of a population, which tells you the variation in your sample. You have to distinguish that from the estimate that you do by applying a model like a normal distribution, and the standard error of the mean. These are all different concepts. Now it's time to move to probability. A probability is a real number between 0 and 1. And the probability distribution that we already have seen, such as the normal and the log normal distribution, is just a list of possible probabilities or possible outcomes. And very important, these numbers, these probabilities should always sum to 1. And the boundaries of this, as if you have a probability of 0 means something will not happen, and a probability of 1 means an event will happen. So there is no uncertainty. It will happen or it will not happen. But everything in between means that we are not certain, and we can only express it in a probability. Now, a frequency distribution that we already have seen for the apples, you can interpret as a probability distribution if you have normalized it. So that's one way of expressing probability. If you collect a lot of samples, then the most probable sample will be the mean. So that's an interpretation of frequency distribution. But there's another way to express probability, and that is uncertainty. We can also talk about uncertainty of things that we did not observe yet. So if I have to predict the weather of tomorrow, I can say that there is a 60% chance that it will rain tomorrow, but I do not have the data. It is just an expression of my belief in what is going to happen tomorrow. And we can also express that in a probability distribution. And I just wanted to give you a few terms that you may encounter in literature. And the first one is joint probability. So imagine, this is just a silly example with just arbitrary numbers. But imagine that you have two variables, A and B, and they can take on three values, A1, A2, A3, and B1, B2, and B3. And these are just made up. What you then look at is the so-called joint probability. So here 0.2 means there is a 0.2 probability, 20% chance that B2 and A2 will happen together. So these are joint probabilities. Then we have marginal probabilities. If we look only at B1, we can then sum up all the probabilities for B1, and we end up with a so-called marginal for B1, and for B2, B2. And the same for A, we can add all the probabilities for A1 and A2 and A3. And also here we see that they have to add up to 1. And these are called marginal probabilities because they are in the margin of the table. So these are the marginal probabilities, something that you will also see a lot in literature. And then we have conditional probabilities. And that considers some more attention because we're going to use that later on. What is a conditional probability? it is conditional on something that has already happened or will happen. So for instance, if we know that event B2 happens, we can consider what is then the probability that A1, A2, or A3 will happen. Well, you can calculate that easily from such a table. So for A1, will be 0.08 divided by 0.34, for A2, 0.2 divided by 0.34, and for A3, it's 0.06 divided by 0.34. That we can also put in a table, and then note that the marginal for probability B2 must be 1, because we have assumed that B2 will happen. So it must be 1. But the conditional probabilities for A1, A2, and A3 are listed here. And they are conditional, once again, on the knowledge that B2 happens. And the notation for conditional probability is listed here. It's the probability for event A1 given that B2 has happened. And here's a real life example again for the apples, where we see the relation between diameter and weight, but we can also look at the marginal distributions, again in the margin of the graph, for the weight, which is here, or for the size, which is here. So this is the way you can display a marginal distribution. So you just integrate or sum up all the other events to arrive at the marginal distribution. Now, there are some rules for probability theory that I just want you to know of. I don't want you to remember them, but just that you know that these rules are here. So there is a complement rule, which means that if probability A is happening, it means that the probability that A is not happening is 1 minus that. You can also have the probabilities of two events together, which is the sum of the probability of each of them separately minus their joint probability. Unless they are mutually exclusive, which means that if one happens, the other cannot happen, then the probability that A and B happen together is just the sum of them. There's a multiplication rule, which says that the joint probability can be split into the probability of A times the conditional probability for B given A, or the probability for B multiplied by the conditional probability of A given B. And if events are independent, so that means they do not depend on each other, then the probability for the joint probability is just the multiplication of the probability of A and B. Once again, I don't want you to remember this. It's just these are very well established rules already for centuries, and they are. I just want you to remember the terms because they will come back later. And that brings me to the approaches in statistics that I like to conclude this first webinar with. But I suggest that we take maybe 5 minutes break now. Is that okay?
Yes, we can take 5 minutes break, no problem. Thank you for this first half of the presentation.
Yeah. Okay. See you in 5 minutes.
So yeah, we should reconvene at 9:55.
Yeah.
So,
exactly.
perfect.
Okay. See you then.
So while we are here, I'm going to remember you that this is the first session of 3, which are going to happen also tomorrow and after tomorrow, again at 9 a.m. Central European Time. You will get a form from my colleagues for register your attendance, and it's needed to attend 2 out of the 3 sessions to get a certificate of attendance. So you will get by email the form to verify your attendance. So yes, now thank you, and I will see you in 5 minutes.
Okay, on my clock it is 9:55, so shall I start again?
Yes, I think
Okay.
you can go on. Thank you.
Right. So it will be a little bit more than 1 hour. My apologies for that, but this is the last part, which will not take so long anymore. But what I have been telling you so far is needed to understand the two approaches that we have in statistics, namely the frequentist approach and the Bayesian approach. And the two are philosophically very different, and that's what I want to explain to you. You all probably have you all have learned, I guess, to do the frequentist approach, even though you may not even know of this term. But that is the way statistics is taught in universities. And the Bayesian approach is usually not. And I also had to learn it myself because also at our university it is not taught yet. But I think it is a very important one, and you will also see more and more papers using the Bayesian approach. So my goal is to let you at least know what it is. Okay, so if you let's start with the frequentist approach. So, for instance, you want to estimate the number of microorganisms in a milk sample, and you can take several samples and you measure it, and then you can calculate the average number and the standard deviation, etc. If you do growth experiments, you can also try to find out other parameters. But the basic thing here that you need to know, if you didn't know before, is that in the frequentist world, these parameter values are fixed. They have a certain value. We do not know the value. That's why we need to make samples and measure it. But the assumption is this value is fixed. And the variation that we observe is not in the parameter, it is in the measurements. And that's why we already have seen it in this frequency distribution. So probability is really expressed as the frequency of events. That's why it's called the frequentist approach. Now, we all know that if we take many samples, they will not give the same average results. But as we also saw, if you take more and more samples, you get closer to that mean. And if you would be able to measure all the samples in the world, so all the milk, for instance, in all the world, then you would be able to find that fixed value. But of course, you know that it's impossible to measure all the samples in the world. And so it is not measured, but it is imagined what happens if you would take infinite measurements. So the emphasis is on the variation in the data, not in the variation in the parameters. And the basic assumption here is how likely are the data in view of the hypothesis that you have. And here is one example of how you can use this in terms of conditional probability. So it is the probability for the data given your hypothesis. So the hypothesis is fixed, and what is the probability that you will observe certain data? That is the basic assumption in the frequentist approach. And it leads to things like null hypothesis testing, ANOVA, p-values, and confidence intervals that you all know, I guess. And there's always this assumption that of the null hypothesis, there is no effect of a treatment. That's why it's called null hypothesis testing. And the alternative hypothesis, H1, is there is an effect. And then you estimate a p-value. But what is frequently forgotten is that this p-value always refers to the null hypothesis, and not, as many people think, to the alternative hypothesis. So the p-value expresses how likely it is to have these data that you obtained if the null hypothesis is true. So a p-value of 0.01 means that there is 1% probability that the data that you collect are because of the validity of the null hypothesis. It does not tell you anything about the alternative hypothesis. Another thing that is frequently forgotten is that a 95% confidence interval does not indicate a probability. it indicates the frequency of observing those data. Yeah, so it indicates that if you repeat the experiment 100 times, 95 times you will be in that interval, and 5 times you will be not in that interval. But it's a frequency, it is not a probability. Now, that brings me to the alternative approach, because what is actually the goal of inference in science? What we really would like to do is to understand the mechanism, the process that causes the data that we have seen. So, but what we learn from the data is only the effect. So we give a treatment, for instance, we grow bacteria, and we measure the effect in terms of numbers of bacteria. But what is the reason we see the numbers increase? That is something we like to know. So what we really would like to do is to go from effect, measuring the number of bacteria, to the cause, what is causing these bacteria to grow. So also, again, in terms of conditional probabilities, what we want to do is to go from the effect given the cause to what is the probability for the cause given the effect. And the effect here is measuring the number of bacteria, for instance. But we really want to know what is happening here that explains that effect. Now, this brings into the picture the so-called Bayes rule, which gives us a way to do this calculation, how to go from effect given the cause to cause given the effect. And this is the Bayes rule that actually makes this possible. It is the probability for the effect given the cause times the probability for the cause divided by the whole effect. Why is it called Bayesian? Because it is named after a philosopher and statistician, and he was also a clergyman, Thomas Bayes, who lived in the 18th century, and he derived the theorem that I just mentioned, and it is called Bayes' theorem by now. But not in his lifetime, because he died before it was published, but a friend of his called Price presented it to the Royal Society of London in 1763, so 2 years after he died, and it was forgotten. But later it was independently discovered by the French mathematician Laplace, and he published it in 1812. So this is again this rule of Bayes. And to honor the man who first thought of this, it's now called a Bayesian approach. So the Bayesian approach, in contrast to the frequentist approach, is expressed as a degree of uncertainty. Yeah, I already gave the example, it might be 60% probable it will rain tomorrow, but I have no data for tomorrow, so it's just a belief. The difference with the frequentist approach is that the data are considered fixed when you have obtained them. And then the question becomes, given these data, how likely is now my hypothesis? And the parameters for instance, a distribution, they are not fixed, but they have a probability distribution, which in this case indicates the uncertainty. We are not sure what it really is. I'm not sure that it is 60%. And I can express that in a probability distribution. The hypothesis that we always should have when we do science is also expressed as a distribution. So what do we think before we even see the data that will happen? And you can express that in a probability distribution. I will explain it in a moment. Then when you get data, you can then combine what you expected from your hypothesis with the actual data, and you end up in what is called a posterior distribution that will tell you everything that you can know given the data and your hypothesis. And this cycle can be repeated. So we can determine a posterior distribution, and then maybe 1 month later, we start again, and we can then use that posterior distribution of the first time as the prior for the next one. So what we are basically doing then is updating our knowledge, because basically we get more data. The Bayesian data analysis is the result of applying probability theory. And that's why I show that to you. What are these rules of probability? They are used in the Bayesian approach, and they basically they're just counting all possibilities that there are in the framework of a hypothesis. And that's why I wanted to introduce to you this concept of conditional probabilities. So the Bayesian approach is about what is the probability of my hypothesis given the data that I have. And remember, the frequentist approach is just the other way around. That's the probability for the data given the hypothesis that they have. Bayes' rule requires 2 or 3 concepts. The prior, so the hypothesis that we have, the data, which is expressed in the so-called likelihood, and we can calculate from this the posterior, the updated knowledge that we have. So how does this work? We'll go quickly through this one. I just abbreviated this. So the cause is now called the hypothesis. The effect is called data. And so I just rewrote this equation, but it is just the same thing. So what we have here is the probability for the hypothesis. This is called the prior. What do we know about our hypothesis? And we express that as a probability distribution. Then we have the likelihood. What is the likelihood of our data? This is actually the same as the frequentist approach. It's the same likelihood function that expresses the likelihood of the data. This is where the frequentist approach stops. It just looks at this one. But the Bayesian approach goes one step further because it also considers the what is called the average likelihood. What is the likelihood of summing up everything that is possible? But this is just a number. It ends up in a number. So it is basically there to normalize this equation. And when we calculate all this together, we end up with the so-called posterior. What do we know about our hypothesis? What is the probability for our hypothesis given the data that we have, based on what we saw in the data and what we have assumed for our hypothesis? And the nice thing about this is it is expressed as a probability density function. So not just one value, like in the frequentist world, where we assume that there is one fixed value. In Bayesian analysis, we get a probability density function for our results. So here you see a little bit of how you can express your hypothesis in prior distributions. So if you are not very sure about a certain value, you can express that in a so-called weakly informative prior. So it's a very wide distribution. If, on the other hand, you know already a lot about your hypothesis, you can make it a very narrow distribution, and that is called an informative prior. And of course, the more informative a prior is, if you go back to the previous slide, you will see that the posterior will be influenced by this informative prior. The reason that Bayesian is so attractive is that you can, by choosing the prior, you can choose from all available prior density functions. So if you know, for instance, that your parameter cannot be negative, you can choose a log normal prior, or you can choose an exponential prior. Or if you know that you have counts, you can use a Poisson distribution for your prior. So it gives you a lot of flexibility to adapt your hypothesis to the actual data that you have. Now, just to finish up, numerical techniques are needed to obtain this posterior. Because the calculation of this denominator, this probability for all the data and the hypothesis together, is almost impossible mathematically. And that is also the reason why you did not learn about the Bayesian approach, because this became only possible with the computer. So that's also why the frequentist approach became dominant in the 20th century. And well, people are trained in that, and they are still teaching that at universities. But since about 20 years, it has now become possible to use this computing power to actually approximate these posterior distributions. And this is done uh, mostly done with what is called the Markov chain Monte Carlo techniques. And there are all kinds of versions one, and this is the state-of-the-art software that is available at this moment. But there are actually many more, but this is called the Hamiltonian Monte Carlo. The approaches compared means, from the frequentist point of view, that you do not use existing knowledge. You are not allowed to introduce prior knowledge. Everything is based only on the data. You can only obtain point estimates because parameters do not have a probability distribution. They are fixed or assumed to be fixed. And this leads then to null hypothesis testing, which focuses on the data and not on the hypothesis. So the p-values refer to the null hypothesis and not to the alternative hypothesis. And these 95% confidence interval should be interpreted as a frequency and not as a probability. The Bayesian approach, on the other hand, allows you to express previous knowledge in this prior distribution. And it does not lead just to point estimates, but to complete probability distributions for parameters that you are interested in. And in the next webinar tomorrow, I will show you some examples. A very important point in my view is you do not need to do significance testing. What is done frequently here in the frequentist approach is that p-values lead to decisions. So if the p-value is smaller than 0.05, we call it significant. It is bigger than 0.05, we call it not significant. But this is very arbitrary, and it's a rule that actually makes no sense. There is no science behind that. It's just an arbitrary decision. And in the real world, there is no distinction between significant and non-significant. And that is why the Bayesian approach is much more valuable in terms of science. You have to make the decision, is this significant or not? So if you find that something is 80% probable, do you find that significant? Or do you really want to go for 95%? That's up to you, not to one stupid p-value. So you can hear from my arguments that I'm very much in favor of the Bayesian approach. So that is true. I learned about this some 20, 30 years ago, and I became very enthusiastic. And that's why I want to share it with you. And I will also show tomorrow some applications. So to conclude, the take-home message for today is that you should take into account variation and try to separate it. Is it biological or technical variability? Systematic errors, as we saw with accuracy and precision, systematic errors cannot be repaired by statistics. So you always have to do proper calibration. Random errors cannot be avoided, so don't try to hide them. You can try to reduce them, but never hide them and mention them. And I hope that you take home from this lecture that probability distributions are really a very important and powerful tool to characterize variability, errors, and uncertainty. And once again, statistics is the tool to deal rigorously with uncertainty. So tomorrow I will apply these concepts in modeling and regression, and also in the third seminar I will apply it into ANOVA, contrast analysis, and a newer technique called multi-level modeling, and perhaps even Poisson regression if I have the time to do that. So that's what I wanted to share with you. I hope I did not overwhelm you with all this information, but let's see if there are any questions.
Thank you again for this nice presentation. It was very interesting actually, and very useful. Yes, I guess we have some questions, and if anyone else wants to add any other question, you can write in the chat or raise his hand, her hand, and share it with us. First of all, I'm going to ask a question myself, and is mainly related to the first part of the presentation. And in many microbial studies, we deal with values below the detection limit,
Mm-hmm.
which usually are recorded as non-detected or below detection limit. How
Yeah.
should we statistically treat these values as zeros, left sensor data, truncated data? Is there a proper way to deal with this kind of data?
Yeah. Good question. I already mentioned Poisson, and I hope that I find the time to do a little bit of more information on that in the third seminar, or maybe tomorrow. I'll have to see how far I will get. But the solution to this is Poisson regression, because Poisson regression actually you can take the zero counts into account. So that is the proper way to deal with that phenomenon. I can. There's also a very recent article that sums it up very nicely. I will also share that with you. But Poisson regression and the modifications of Poisson regression are the solution to this kind of problem. And especially indeed for lower counts, this becomes quite important.
Okay, thank you for the answer. I see other question here. Well, one very general is what are some common mistakes beginners make when applying basic statistical methods in food science, if you can think of any?
Sorry, come again. What is the
There's some
question?
common mistake the beginners
Ah,
make.
yeah. Okay. Yeah, yeah. Also a nice question. Well, the mistakes I see often is that people try to hide variation. So for instance, you can express your variation in a standard deviation or in a confidence interval, whether it's Bayesian or frequentist, and then people tend to go for the standard deviation because it's smaller. So they are trying to hide the variation, or they are only showing averages. I'm a big fan of showing all the data, all the raw data, so that people can reproduce the data that are found. Um, and this is especially true for open science, because science should be reproducible. Others should be able to reproduce your conclusions and maybe come to different conclusions if they have the same data. So I think that is the most common mistake, that people try to hide the data just to find nice results. The other mistake is what I already mentioned about the p-values. People use p-values to say that something is significant or non-significant. And especially in foods where everything is so variable, it is usually not a matter of is it significant or not. It is more you should think about, is this, how likely or how probable is this, and not so much this is yes or no. So I think those are the biggest mistakes that are made. And the third thing is that people are just using statistical software by clicking on something and then get a result. You always get a result and publish that without really knowing what it means. And so I think that many people think that a p-value tells you about the probability of an alternative hypothesis, which is not true. So there is a lot of mistakes made because people do not really understand the concepts behind it. And that's why I also wanted to show this today with rather basic things to to try to explain to you what they really mean, these concepts. So those are the three basic mistakes I often see.
Yes, I think most of the time we get caught most on proving the significance of something rather than the relevance of,
Exactly.
of this
Yeah.
this thing.
And I find
Um,
that very sad, because I think that a lot of very useful data are not even published because people think it's not significant. Well, I think it's very important to know this. Even if it is not significant, I like to know that. And I also blame editors for forcing people to do it like this. I think it's not a good practice.
yes. Well, a few other questions I see here. Well, one, even though I understood that you're a big uh, fan of Bayesian approach, is there some situation in which frequentist approach may outperform Bayesian or is preferred to Bayesian approach?
Um, No, I will also tell that tomorrow. Let me also make clear that the frequentist approach is not wrong. It's frequently misinterpreted, but it is not wrong in principle. So there is not really a, a, a principal difference in when you should use frequentist or Bayesian approach. There are things that are in favor of the Bayesian approach in terms of that it gives you much more information about your parameters and your hypotheses. But it's computational. It's quite intensive, and you really I will also tell that tomorrow. But you really have to do some programming in order to make it happen. So the frequentist approach is much easier to do because all the software is geared towards that. Um, but what I also think is very important that because we can use prior knowledge in the Bayesian approach, we don't need that many data. So that even with very few data, you can come to a conclusion, and that is not possible in the frequentist world. So there are some reasons why you should choose Bayesian or frequentist, but I will also show tomorrow with regression that usually the outcomes are the same, but the interpretation is different, and that's the key, I think.
So it's basically a different process to go to the same result.
Yeah, exactly.
Is there like an established way to apply the Bayesian approach when building, predictive models or predictive microbiology models? Because we're maybe more familiar with the frequentist way of doing it.
Yeah. Well, tomorrow I will share 3 tutorials that I wrote to how to do this. Um, because I do not have the time to show that in a webinar. But the actual way of how to do it, I can give that tomorrow to you, so you can practice for yourself. It's also again very simple data, but you need some software for the Bayesian approach. You either need to work with R or with Python or Julia, which is a newer language. Um, and the frequentist approach is done in almost every software package that does statistics. There are also some commercial packages like MATLAB and Mathematica probably that can also be used to do the Bayesian approach, but they are very expensive. And R and Python are for free. But you need to do some programming. That is the downside of it.
Yeah. Thank you.
But I will show you tomorrow how it looks like. It is not it sounds more complicated than it is. There is really good software to actually do it. But the basic thing is and that I find very important in the Bayesian approach. You have to specify your likelihood and you have to specify your prior. So it means you really have to think hard about your data. And you really have to think hard about what do I know about this before I even see the data. And that you really need to specify. And that is hard thinking. I mean, and that is also something that people, the first question was about the beginner's mistakes. I think that is also a sort of beginner's mistake that you want to show results immediately without thinking about what do I actually want to know. And the Bayesian approach forces you to specify that.
Yes, I guess that specifying prior knowledge is not always easy. Make assumptions about your data.
Yeah, exactly.
Okay, I see one last question, unless anyone else has something to add, which is if you may answer, what are the main challenges in incorporating artificial intelligence into predictive models? I don't know if you're going to talk about this later in the seminars, but that was one last question.
What's the biggest challenge? Was that a question?
Of incorporating AI into predictive models.
Okay, AI. Okay. Well, I'm not very knowledgeable about AI, I have to say, but what I do see is that people in my environment they frequently use AI to solve some programming problems. So you can also ask AI to write programs for you in R, for instance. And that is, I never did it myself, but because I want to understand what I write down. But I know that people are doing that. And undoubtedly, there will be AI has enormous potential. So it might well be that this is going to conquer also for the Bayesian part the world in that sense. But my biggest fear is that people are not knowing what they are doing then. They all leave it to AI, and then the assumptions behind AI are not clear. What are they doing and why? And that is something that I am a bit hesitant about. But I'm quite sure that AI is going to be important.
Yes, thank you for this intake on the topic. Yes, probably that's the main issues. As you said in the beginning, people do the same with softwares, and probably
Yeah.
AI is a bigger version of this problem. But
Yes,
yes,
I guess so.
it's for sure has some great potential.
Yeah.
Well, thank you again for all these nice answers and for the presentations. And
Yeah. Can I also ask for feedback if someone not
yes,
necessarily now, but if people want to comment on what I said, was it boring? Was it useful? Was it too long? Was it too short? All these things I like to hear. I really like criticism because I can also learn from that. So if people want to write something, I will be happy with that.
also if you want to comment anything, you can raise your hand and try to speak up now.
Yeah,
And
that's also fine. Yeah.
yeah, yeah, I see some comments in the chat. Very useful. Thank you. And also, I will invite all the participants to open their camera to take a picture at the end of the presentation. If you're willing to participate in this, I will thank you. And while I wait, I will remember you that tomorrow is going to be held the second session of this webinar, again at 9 a.m. Central European Time. And yeah, if you have any technical issue or any question, feel free to reach out to the committee. Okay, I see a few open webcams. You may now stop sharing your screen if you will.
I will. It stopped sharing. Yes, of course.
Yes,
Stop screen sharing. Yeah. Okay.
perfect. Okay, so my colleague will take a nice screenshot to publish, and Natalia, let me know when you're ready.
Okay, so please everyone open your camera and make a big smile. Let me try to fit everyone here in the screen. Wait. Let's see if I can do it. Okay, so let's try 1, 2, 3, and cheese. Oh, I'm not sure that went well. Let me check.
Well, thank you anyone who participated today, and I hope to see you again tomorrow. And I hope you enjoyed, and thank you again, Professor, for this nice presentation.
You're welcome. See you tomorrow.
See you tomorrow.
Thank you so much. See you tomorrow, everyone.
Bye.
Bye.
Thank you. Bye bye.
Bye.